Yes, indeed.
All right, that sounds great. Yeah, it's been very nice weather-wise and just very enjoyable. Hi, Arthur. How are you?
Hello there. Oops. There we go.
Any thoughts on what we went over last time? I know, Arthur, you weren't here, but we did cover initial sort of sorting, very simple techniques of sorting by counts. Essentially like figuring out the rank of the eventual value.
Yeah, I was just watching a little bit of the recording. I only got like, half an hour in or so, but I liked Michael's bubble sort and rock sort, by the way. I also had not heard of rock sort, but it makes sense. Bubbles go up, rocks go down. I get it.
I'm surprised nobody's heard of that. I actually, there were two ways of doing the rock sort. Okay, and the way that I think about it usually is you go on the first pass, you examine every item against the bottom item, and if the item that you found is bigger than the bottom item or the last item in the list, you swap it. So at the end of your first pass, you're definitely going to have the largest item on the bottom or at the end of the list.
See, that I would call selection sort.
The other way is to take 2 pointers and walk the 2 pointers from the first and second element of the list down to the very bottom of the list, and every time those, so the 2 pointers are always sequential.
Right.
And if they are out of order, you swap them.
Yeah, to me, that's what bubble sort is.
Okay.
Or I guess rock sort if you go the other direction. But to me, bubble sort is specifically, it bubbles things up, in a bubbling motion. And so you're right that if you're going upward, the biggest one is definitely going to end up at the top. But you are also, meanwhile, doing some work on the lower ones.
Right.
And in fact, bubble sort I'm familiar with, you don't even optimize it by like, now the biggest ones at the top, so you can just do the n-1 elements and n-2 and n-3 and so on. But
exactly.
What we see is it just 2 loops, both going from I equals 1 to n, j equals 1 to n, and then just, number of iterations going from 0 to n, and then for I equals 0 to n, maybe swap I with I plus 1. And you just do the entire thing, and that's one reason it's inefficient, is the naive version does twice as much work as it needs to, even before you get to the fact that it's quadratic.
Okay, well, there's one other important difference that I realized over the weekend between those two. The one that walks the 2 pointers down, that's a stable sort. The other one's not stable.
The selection sort, you mean, is not stable.
What you're calling a selection sort is not stable. To me, a selection sort is moving the elements into a second array. But I mean, it's just semantics, really.
Well, to me, selection sort is you find the maximum and put it at the end. You find the max minus 1th and put it at the n-1 position.
Okay, it works. It works.
Or the other way, right? Find the smallest, put it at element 0. And so selection sort is basically a recursive, the way you sort a list is you put the smallest one at the front and then you recurse.
Hi, Jolene and Miguel. Welcome.
Hello.
Hope you guys had a good holiday? Very nice. Well, bubble sort is going to be the topic of next weekend. We'll start with basic bubble sort, and then there's a couple of variants on it, but that's next week. And today it'll be insertion sort, which we'll start out with. And if you remember the first section that we read last week, Knut had sort of categorized the various approaches or techniques you can use to sort. And so we're just going through that list. I realized later that there were actually a couple of introductory sections that we had skipped. So I'd like us to start with those. They're easy reads, so we'll spend about 5 or 10 minutes on that. There's a preface to the entire volume. So we did start a new volume. And then there's a little introduction to the chapter of sorting. So I think we can go ahead and start. So that's the agenda for today. And so after the basic insertion sort, there's an algorithm for that, and then there is an MMIX program as well. I think the MMIX program is pretty straightforward, but there are a couple of things that maybe are interesting to discuss, especially in terms of the cost of the algorithm. I think it's becoming more interesting now to talk a little bit, at least whenever we get the chance, about the cost of these algorithms, because we're solving the same problem over and over again using different techniques. And so it should be, I think, pretty useful to have that comparison and understand, what the trade-offs are. So for that, we're going to look at, if you've noticed in the MMIX code and also in the older MMIX code, there's a column for instruction counts. So with every line, there's a number, usually some variable number, and that tells you how many times that line will run for some particular input. And so I think we should spend a little bit of time talking about those numbers, because Knut does summarize the cost in terms of those variables, so it'll be good for us to have that foundation as well. So that's there, and then we'll conclude with a variant of or an enhancement on insertion sort, which is called Shellsort, named after Donald Shell. And so we'll look at that algorithm, and then afterwards, hopefully we'll have some time for exercises. But after the main session, then I will do step-throughs for both the program S, which is the MMIX program for the straight insertion sort, as well as for Shellsort. And Shellsort is just like a tweak on insertion sort. So once you understand insertion sort really well, then I think you can appreciate Shellsort pretty easily. So that's the plan. And everybody here is familiar with our process. So we'll get going with volume 3. And we're starting with the preface to the entire volume. So this is Roman pages 5 through 7. Spend just 3 minutes on this. What do you think?
Well, he doesn't like software patents.
He doesn't like software patents. Yeah, yeah. And what do you think about that stand?
I tend to agree with him. I was just looking at the, he cites C section 545 there on that statement. It turns out that's a part of the book where he's discussing an algorithm that is patented.
Which one is that?
Somehow related to a patent, oscillating sort.
Oh, okay. Yeah, it's also interesting to see his plans 17 years from then, which was 1998. So he's a little behind, but he's still completed a lot. I would say that he's probably gone beyond what he even expected in terms of what he's actually done for volumes 4A and 4B.
Well, I think this was before he had decided to do MMIX at all, right?
No, this is an edition that came out after MMIX, but he had said that he would not be able to add the MMIX code in time.
Right.
But MMIX, I think the supplement, I mean the fascicle 1 came out maybe around the same time or maybe a little earlier.
But the thing from 98 is actually the second edition. So actually, it's the third edition that had MMIX, I think.
The third, I don't think there's a third edition of this volume.
Okay.
That's the third edition of the first volume that you may be thinking about.
Yeah, I am.
Okay. Anyone else? Any other thoughts on on his initial sort of the coverage of the important general issues? Okay, well, that was just supposed to be an introduction to the entire field in some sense. Let's move on to the introduction to the chapter itself, chapter 5, sorting. This is pages 1 through 5. Okay, how about this section? Anything to comment on or clarify? Did everyone get to the last page where he has the definitions of the ordering, the linear ordering and stable sorting and the terminology?
I hadn't quite finished the last page.
Okay,
but
we
I
can
was
spend a
pretty-
minute more. Yeah, one more minute. Okay, feel free to comment whenever anyone has anything to say.
Well, I'll say that I liked his list of important applications of sorting, which are all distinct, and I agree with all of them. Coming from a C++ standard library background, I know there are sorting algorithms, or maybe I should say, the algorithm sort can be used to solve all of these problems in different places, especially B, which he calls matching items in files. In C++, we might call that the set algorithms. Like if I have two sorted lists, then I can merge those two lists in linear time. I can, if they represent sets, I can union the sets or intersect the sets or compute the difference of the two sets in linear time. And so that's nice. Also, so a solution to C, searching for information by key values, involves a solution to A, solving the togetherness problem, because you want all of the answers to be together, right? If you know where the answers are, all of the answers ought to be there. But you can also solve A without solving C. And so I thought it was interesting that those are in some way independent problems. And I'm not sure where B fits in.
Yeah. I mean, it's very unlikely, but can anyone think of some type of problem that sorting can help with, but is not covered by one of these three? Has Knuth done a pretty exhaustive classification?
Well, there is finding extrema, finding maximum and minimum. It's not the most efficient way to find the maximum and the minimum, but it's certainly used in practice a lot to find the maximum.
Yeah, that you actually bring out a good point, that sorting, and just because it's so easily available in whatever environment that you're working in, right? Every platform, every language, every system provides a way to do efficient sorting. And so it can sometimes even become a crutch. It's sort of like it can become your first go-to response. Oh, first I'm just going to sort, then I'll think about like how that could help me, because sorting just imposes this order that makes it easier for us to think about things and reason about things. So it can become a crutch. But because generally it is pretty fast and efficient, you're not going to be that bad off if that's your first attempt at a solution, I feel. But often you can, if you really understand the problem, you may be able to find much better solutions without sorting. So, yeah. Any other comments? Anything about the terminology again, or any of the concepts?
For the last sentence, so if you know something about the distribution of the keys, you can accomplish it in n time. I was wondering if that's something to do with the algorithm for sorting that you were discussing last week, the distribution sort. Is that an example of that?
I would say so, yeah, because we did find out that that was a linear time algorithm. I think we made 2 passes through the array for that algorithm. And that's entirely based on the fact that you knew that there was a minimum and maximum on the range of the numbers. And so you're able to create these special slots corresponding to those values. And there's many other examples of that, many interesting examples that we'll see later on as well. And if anyone knows, of specific examples, please feel free to offer them right now, where knowing something about the data set can help you sort faster than n log n time.
Yeah.
Yeah, I mean, there's definitely things like the counting sort and radix sort that rely on the keys actually being small integers, right? Not just comparison based, but some structure to the keys.
Yeah.
But I don't think that's what he's talking about here. I have no idea.
Yeah, actually, I think your condition has to be a little bit stronger than some continuous numerical distribution. Maybe some continuous numerical distributions work, but I don't think a random continuous, if the continuous distribution ranges over 35 digits or a lot, ranges over a large time, and you don't have that many elements to sort, it's not going to be order of n.
But what do you think about the point from last week that you could still use some digits, right? You could still use
Yes, that definitely works. So when you're talking about a key that's only a digit or two, it can definitely be done in order of n time. I think that's the point he's trying to make. But what I'm saying there is that he's saying if the keys are known to be randomly distributed with respect to any continuous numerical distribution, he didn't put any in there, with respect to some, certain continuous numerical distributions I could live with, like certain would include distributions that have a very small range, or there's probably other distributions that you could find an algorithm for, but not any.
I'm interpreting his word some to mean any. I don't see how he does it, but I believe that he's going to do it. But I assume that some means any here. Not there exists one particular distribution for which it works, but...
Well, I would say there exists certain distributions for which it works, but not any random distribution.
I think that's what he's saying.
Okay, well
he's also saying
I don't know what that would be.
Remember,
because you could certainly put the elements into buckets with a large distribution, but then you'd have all the empty spaces in between the buckets.
So you'd have to say, well, how many empty buckets do we expect, given that the distribution is continuous?
Let's say I had 10 items to sort, but the items that I had to sort were 100 digits long. If I use that bucket sort, I would end up with an array of 10 to the 100th elements with a lot of blanks in between, and I'd be spending order of the size of that array, order of the size of that distribution, not order of 10. You see what I'm saying?
Well, I think what you would do is, number one, you wouldn't have 10 to the 100th buckets. You'd only have n buckets, right? And you'd make the sizes of those buckets proportional to the distribution.
Yeah.
So I guess we say if the keys are known to be randomly distributed with respect to any continuous numerical distribution, and we know what that distribution is, then we can make our buckets match the distribution.
Okay.
The way
but what I'm talking about is sorting 10 numbers. They're 100 digits long. Okay, that satisfies the condition as he wrote it there.
Right.
A continuous numerical distribution. I'm only picking 10.
Right. So in 10 steps, I claim what you do there is you make 10 buckets, and you just look at each number and you say, well, which bucket does this one go in? And at the end, like overwhelmingly likely, right, if they're actually randomly distributed, we'll end up with, one in each bucket, or maybe 2 in one bucket and none in the other. But the chances that all 10 of them wound up in the same 10th of that range.
No, I'm not talking about that. I'm talking about now you have 10 buckets, but they're in random places. How do you figure out which one's first?
Then we're not describing the same algorithm. When I think of a bucket, I think like a hash bucket, where I have 10 buckets right here.
Right, even a hash bucket. If the hash space is 10 to the 100th, I can find any given bucket in order one time, but I can't find the next bucket in order one time.
So what I'm describing, let me try to draw this out here. We've got, I'm going to give 4 buckets because that's how many tick marks I do. And then from this bucket goes from 0 up to 0.25 e to the 100. And then here's 0.5 e to the 100, and here's 0.75 100, and here's 100 all the way at that end, right?
Oh, you're saying hash. You're not saying hash. You're saying okay.
I'm not calling hash bucket. I'm just saying this is analogous to hash buckets. We have 4 buckets here, and we look at that first number, and let's say it's 0.6 times 10 to the 100th. We put it in the bucket. This one here, probably.
Got it. Okay.
Right? And at the end, overwhelmingly likely, all of the elements end up in different buckets, or maybe 2 of them in one bucket and 1 in the others. And I'm not doing. I bet it's not.
I understand.
But the point is the error. If the distribution is actually, uniformly at random, hopefully the errors work out such that correcting those errors and saying, okay, well, now we have 2 things in this bucket that we have to compare, happens less than n times. Right? Happens small enough that the overall running time is basically you do it takes n time, and then you have some small fix-up.
Got it. In that case, it's because you made your buckets so wide that you'd probably end up with a lot of them having more than one key.
But we only have 4 items, remember.
Yeah, you have 4. You have 4. They're not all going to go into a separate bucket. Some of them are going to be. It's like rolling a 4-sided die and coming up with 1, 2, 3, and 4. It's not going to happen.
Okay, that's also a good way to look at it. Anyway, I am convinced that he says this for a reason. I don't think he throws this out there.
Maybe. We'll see. I think maybe you're right.
Yeah, I do think that, and it's really great that he introduces this really early on as saying that you don't have to come up with a technique that, with a single technique, right, that will solve your problem really efficiently. Sometimes you can just use your knowledge about the problem space to help with the solution, right? So achieve some sort of partial efficiency and then maybe reduce the rest of the problem to something that's much more tractable. Okay, so let's go on to the actual algorithms now. We will start on page 80, which is sorting by insertion. And there's a little paragraph before the algorithm, but we'll do the paragraph and the algorithm together for about 7 minutes till 2:43.
Everything goes backwards.
Okay, do we need another minute or two, or are we good to discuss? All right. Who wants to go ahead with the flow chart, maybe?
I can give it a try.
Great.
Let's see. So the goal is to assume we start by, I guess, with 2 elements or something. So the goal is to assuming that all the list is already sorted. We want to add a new element to it and putting it in the right position. That's the whole point. So there is no mention about the list being empty or having only 1 element or anything. It's just there is more than 2 apparently. And then so you start the second element of the list and check the previous one and see if they have to be swapped or not. By swap I mean if the new element is bigger than the previous one, it stays like that. It stays there. If it's less than the previous one, it goes before that previous one, and you move that one slot. And you continue doing that, increasing j. And every time you increase j, you go backwards, comparing each element, and once you find a position where the new element is smaller than one of the previous ones, you move the whole list and insert it there. So that's the whole point of the algorithm.
Okay, could you then also explain table 1? Maybe just 2 or 3 lines of that?
So, sure. Let's see. I guess we begin with. I'm not sure what the little sign is supposed to mean, or the colons.
I think the colon is the comparison point.
It's the comparison point.
Yeah.
I see. So you're comparing file 3 with 87. Therefore, 87 will go in front of file 3. Then you are inserting 512. You compare it with 503, and it's bigger, so it stays what it is, what it was. It stays at the end.
Okay.
Well,
Then comparing. Sorry, what?
Go ahead.
So the next one is 61. So we compare it with. Actually, now it's realized that I didn't. Oh, you compare it until it's bigger than the previous one. Oh, great. So you compare it with the 512. It's less than 512. You keep moving until either 61 is bigger than the previous one, or you hit the beginning of the list, which is what happens with 61. And so on. I guess it's very repetitive from there on. Like the whole point is that you move down the list until you find an element that is, smaller than you.
Okay, that sounds good to me. Anyone else have comments?
I think that as I just said in the chat, I think the deal with the colon in the table 1 is saying, like, we've sorted up to the colon, and then the element after the colon is the next element that we're looking at. And the caret underneath part of the sorted array is saying, this is where we're going to put it, right between these two. And then in the next frame of the animation, you've got it in its right place and everything else shifted over, and you've got a new element after the colon. So he's skipping the bubbling down portion here and just sort of jumping straight to, okay, where's the next one go?
You could read it as K equals 087, which you get into S2, or K equals 512. And then the caret is the point where you found where you found I guess it's S4. That's the
No, it says
that's the
it says
point.
three,
Where
right?
you
If
found,
K,
that's the point where you found where the K is less than the element that's after the caret.
isn't it the opposite? Is it in S3 when you find that K is bigger than Ki?
S3 moves the caret one step to the right because the K is bigger than the element. So like look at line 2 and you're working with 512, the caret will start at just before 087. And in S3, you're going to say 512 is bigger than 087, so move the caret 1 point to the right.
Right.
Well, yeah, but because in S3 there is a branching, right? So
in both cases, there is the
right.
caret.
So if that doesn't,
we go on to S5. We might get there from S3, or we might get there from S4. But it's where we go on to S5 is where the caret comes in.
Yes.
Yep, okay. That is good. Let us now look at the code. I don't want to spend a lot of time on this because I will be doing the step through later on. And so, you know, we can spend a lot more time on the actual MMIX at that point. But what I found interesting was, again, thinking about the instruction counts so that we can better understand the summary cost that Knuth, provides at the end of the algorithm. And so for that, you'll need to go back to the sort of introduction. What was it called? The style guide, I think, or program style guide section of the MMIX supplement. And there's one section there called instruction counts. That's on page 11 in Roman. You can read that before or after the MMIX code. Either way is fine. And then the code itself is also in the MMIX supplement on page 76. So we have about 7 minutes on this. Okay, what do you think? Does the code, did it have any surprises compared to the algorithm? How about the instruction counts and the formula that he comes up with at the end? If you're looking at anything right now, just feel free to to talk about it. Just bring it up and we can discuss it.
Certainly, this is getting mathematical for me. I'm looking at his A and B, and he's right that he discusses A quite a lot in Volume 1, which I skimmed very quickly over and got nothing out of. But A was basically if you're computing the maximum or the minimum of an array by like keeping a running maximum as you go over, how many times do you expect that to change? And he computes the expected value and the variance and so on of this quantity.
Yeah, I think you're referring to the little maximum algorithm that we had discussed, just the algorithm, and then he had that whole introduction to analysis of algorithms in there that we skipped. At some point, I think we will need to cover that section. I'm not sure exactly when, but
so he's basically reducing this to that plus, I've already forgotten what his B is here, but there's a similar analysis for B and figures out what its expected value and standard deviation are.
Yeah, so those are definitely, things that you need for the analysis piece. But over here, there's no analysis so far. It's just counts. And he's just defining A to be a particular count. And what he's saying is that if you look at step S4, this is the way I understood it, that if you look at step S4,
right. Or like line 6 of the, well, I'm looking at the mix code. I guess I have to look at the MMIX code.
In the MMIX code, it'll be line 11 through 13, essentially. Everything after the branch on line 10. So if you fall through that, then you're in lines 11, 12, and 13. And what he's saying is that the number of times I decreases to 0 in step 4. That's what he's calling A. And I believe that these names, A, B, will be very specific to each algorithm and each piece of code. So I think that he tries to be consistent, like he'll use similar names across different algorithms, but their exact meaning could be slightly different. So what we need to figure out here is how many, what does that mean? The number of times I decreases to 0. When would that happen, for example?
That happens when running minimum changes.
Yeah.
Over each thing here, and whenever we need to put one all the way over there at 0, that means it's the new minimum.
Right. If we have to go to all the way to the beginning of the array from our start of the comparison point. That means that the new value that we wanted to insert is the smallest one yet seen. And so it's the new minimum, as Arthur says. And so we don't know how often that will happen. That will depend on the data set itself, right? How the values are distributed. So he's just giving it a name. He's just saying that's whatever that number is, I'm going to call it A. And I know that when that happens, this piece of the algorithm or this step of the algorithm and then the corresponding lines of the MMIX code can be labeled with that count. He can, once he's given it a name, now he can use that name for specific lines. And that's what he's doing with each one of these. With the instruction counts that have n in them, I think those are pretty easy to understand, right? So there's like some initialization and there's an instruction count of 1 there because that will only happen once. And then the rest of the time, if it's sort of a linear scan loop, these lines will run n-1 times. So that's also pretty obvious, I think. But where things get really tricky is when there is some decision point. Like you could go this way, you could go that way. How do we count how many times which fork are we going to take? So he's just giving them different names. And so A is one of them. Did everyone follow the notation where you have a branch and then you have a count in the instruction count column, but then there's a subscript with the brackets, and there's some variable or some expression in that bracket? Could somebody explain that? What does that mean? So for example, line 13 in the MMIX code.
I believe you put that on branch instructions when it's like we can branch this many times, but the branch itself is executed this many times, but it actually does the branch this other many times.
Yeah, in fact, I think line 16 is a little easier to understand that because line 16 is pretty straightforward. That's the branch on the outer loop. That's basically like a for loop, j going from 2 to n. And so the instruction count there, he's saying, is going to be n. We're going to take this, but there'll be one time that the prediction will be wrong, right? When the loop terminates, essentially. That's when we'll fall through and just return from the subroutine. And so that 1 in the brackets is referring to the number of bad predictions that will happen. And for a loop like a straightforward for loop, you'll just see a 1 in brackets there. But for something that's a little more complicated, in terms of branching, like you can't necessarily predict how it's going to turn out. It would depend on the data set. Then you may see something like an expression within the brackets. So that's there. So again, I just wanted us to become a little familiar with that column and the expressions. We don't need to spend a lot of time trying to figure this out or understand it, but it's there. If you want to spend time on it, then it does get interesting, especially when we start to compare the costs of different algorithms. Anything else to point out?
Did anyone figure out what it means by H sub n? I couldn't figure that out.
Which one is that?
H sub n, capital H.
Where's capital H?
In the analysis.
Oh, in the analysis, okay.
In the average of A, it says H sub n minus 1 on page 82 in the formula.
I didn't notice the H. I know that there's an H in the Shellsort algorithm, but H sub n, I'm wondering if that's some mathematical function. Some known mathematical function. Where's the h coming from? That is weird.
Well, it covered from his discussion in 1.2.10, but even over there, I was trying to find it and was not able.
Okay. Okay, well, something to look into. If I figure it out during the break, I'll definitely tell you guys. I did notice a couple of typos here. So line 4 of the MMIX program, where it says initialize j to 1 in the comment, I think that should be initialize j to 2. And similarly, line 16, we should be running the loop from 2 to n and not from 1 to n.
Is that just because of 0 indexing versus 1 indexing, though? There's too many books here. I need bookmarks. What page is this?
You may be right, but my feeling was that when you may be right. You may be right that now in the code that he is using 0 indexing, so the comments maybe match that. But generally, I've noticed that he tends to, in the supplement, match the algorithm as well. But yeah, that may be right. Okay, so we are a little past 3, and so let's take a 10-minute break to about 3:20.
Alrighty.
Okay, we're back. And yeah, whenever you get back, if you could just continue with the next short section, which is a couple of tweaks to the straight insertion sort that's discussed, but not in a lot of detail, but it'll set us up nicely for Shellsort. About 3 minutes on this. Okay. What are your thoughts on the IPM 705 tumble instruction? Yeah. I think you'll need to dig up one of those manuals again. There's probably some photocopied version, copy of the manual that would explain this. So how about these enhancements? Were they pretty straightforward? The two-way insertion? Okay, then let's just go on to Shellsort. So this next section is just sort of a general introduction to the approach that's taken. And it has a couple of really nice tables that show the movement of the data in there. So let's first look at that, spend about 5 minutes on that, and then we'll discuss it and go on to the actual algorithm. Okay, could someone summarize Shell's method?
It's kind of a strange divide and conquer. It's kind of a strange divide and conquer where you take, you divide the file up into, well, in this case, 8 pieces at first, and but it's like you're sorting 1, 9, 9 plus 8 is 17. You're sorting those, and and then you're sorting 2, 10. I guess in the example here, it's just 2, but it works with any. I mean, you're sorting 8 groups of 2 elements each, but it could be 8 groups of 3 elements each if the sequence was a little longer. It doesn't really matter. Although you might, if you had a table that's much longer, you might start with 16, and you would. The idea is that if you can sort 8 groups of 2, then you'll be bringing the smaller elements to the beginning of the list, and the larger elements will go to the end of the list, but they're not quite in order. But it's going to be a lot easier to perform insertion sort because when you get down to the lower steps, there will be less changing to do.
Did you have any problem with the intuition behind why this would be useful? Like what are we gaining from this complication?
I certainly had trouble with it at first, but I think I'm starting to get it.
Okay.
That we're basically taking 2 sorted arrays and interleaving them. That is what we end up with after one of these steps. And then we're trying to insertion sort that merged set of 2 arrays. And that seems like, well, that's still insertion sort. We're still having to, like, for each element, bubble it to its proper place, and then we're shifting all the other elements down, and that's still quadratic. But I think the trick is that because that element is now roughly where it should be, because it's part of a sorted half of the array, and we assume the elements are all independent, it really doesn't have n over 2 spots to go on average. It has more like 2 or 3 spots that it needs to move. And so that removes a factor of n. And I guess it must add a factor of log n somehow. Or no, removes a factor of n from there, but then we have to do this whole process log n times. With 4, and then we
Are you suggesting that this will turn out to be n log n?
I'm hoping so.
Yeah, well, your hope, I'm not sure if it's proven, but I think the best so far from what I read is n log n squared. So just the log n times log n. So I think that's the best that's been found so far. Yeah, go ahead.
Oh, I got nothing.
Okay. So my intuition was really to just focus on what Knut said about minimizing the movement by making the keys jump as much as possible in one go. And so in straight insertion sort, every key that moves will move 1 step at a time to whatever its eventual place is going to be. And, so that's just unavoidable. But what if, it's going to get to wherever it needs to be, but what if you could make it jump there in, bigger jumps, like instead of 5 1-step jumps, you could do like 2 jumps, 1 of 2 steps and 1 of 3 steps. And so that's sort of the idea that I got, that, if we can somehow compare things that are far away, then maybe we can minimize the number of 1-step jumps that each value will need to take. It may still happen, but there's a good chance that we can reduce the number of these steps or increments. Anyone want to comment on that?
I mean, that's the rationale that I'm in trouble grasping, thanks to my obsession with corner cases. I mean, I look at the table 3 here on page 84, and, when I look at this, I see that, like, 503 started in the first position, and after all of these conditional exchanges over long ranges, it turns out 503 is still only in position 3 and has to be bubbled all the way down to where it needs to go. And on the other end, we actually swapped 897 in the wrong direction and had to bubble it back up. And so my brain wants to tell me, well, I don't know if all of this swapping is helping. But I think that it does. I think on average, these long swaps should be helping.
Yeah, but if you look at it, this table is 16 elements long, so you would expect in that last part, if you just did that most elements would have to move by 8 positions, and many of them in that last pass only have to move 1 or 2 positions. I don't think any of them have to move as many as 5.
Right, but that's because we've done. I mean, and obviously this is true, right? I'm just telling you what my brain is telling me.
Yeah.
It's that the earlier passes are certainly getting it into more of a sorted state, but then we still have some work to do. We've done some work. We have more work to do. It's not clear intuitively how that maps onto what if we just did all the work.
Okay, so knowing now the approach and knowing straight insertion sort, could someone just describe what we're going to read next, which is the algorithm? Like, how would insertion sort need to be tweaked or modified for it to work as Shellsort?
You're going to need that external table of diminishing elements, or you're going to need a function to start with 8 and have it.
Okay, so assume that we have a fixed sequence like this one, 8, 4, 2, 1. We just have that, present as an array. And then,
if you're going to always use powers of 2, then you wouldn't need it really an external table. You just need to have some function that would give you the next number in that sequence, which in this case is just divide by 2, and some function that gives you the initial number, which can probably be done some way with, given the size of the table that you're going to sort, you're going to have to start with some initial number.
how would the loops change in insertion sort?
Well, you have an outer loop that is going to do it by 8s, and you're doing an insertion sort on what is there by 8s, and then you're going to loop again with the 4s. And
Okay, so the outer loop increment would change. How would the inner loop change?
well, they'd be different. You have your outer loop is going to say 8, 4, 2, and 1. So
what about the inner loop, where you compare it? Once you've fixed one key, you pick your first key. In this case, it'll be, if you're starting with 8, it won't be at 2 anymore. It'll be at 8. And then 9, right? It'll be 9. Yeah. We're starting with 1. And then what are we going to start to compare it to? Like what index will it be first compared to?
If you're doing the insertion sort, then you're comparing 9 and 1.
Okay. Okay. Yeah. So that's
and then
yeah,
9 and 1 and actually it's kind of a degenerate case, because if you're looking at the table, there's only 2 elements. So it's not, for this first iteration of the loop, there's only 2 elements. It's 9 and 1, and then there's a middle loop there that's going to say, okay, we're working on, the outer loop says we're working on separation of 8, and there's an inner loop that goes through 1 and 9 on the array, because 1 and 9 are 8 apart. But there's a middle loop that says we're going to start at 1 and do 1 and 9, and we're going to start at 2 and do 2 and 10. So I see 3 loops in it.
You see 3 loops. Okay. Well, let's read the algorithm. and see what matches up with our guesses so far.
Oh, okay.
Okay, so did the algorithm match up with what you expected? Could someone summarize? Basically, how is it different from insertion sort, straight insertion?
It's basically got insertion sort as a subroutine. Like step D1 is new, and I think D2 through D6 are the same as S1 through S5, with the difference that instead of I plus 1, we're now saying I plus H, where H is the element of the sequence that goes 8, 4, 2, 1 in the example.
So you could easily imagine that step now turning into a parameter to some function. So instead of doing a plus plus or plus 1 or minus 1, you just do a minus H or a plus H.
Right.
Any other comments? So everyone pretty comfortable with Shellsort? Okay, so we can look at some exercises. There's, the usual question about any sorting algorithm. Is it stable? So is insertion sort stable? I think this is exercise 1 on page 102.
Actually, there's one more thing on page 87-ish. Where was this at? I skimmed through the math. Guys, please.
Sure.
Page 90. Page 90, Theorem K says if you do this insertion sort subroutine with a certain step size, then you end up with something that he's calling K ordered, right? You've done it with step size K, so now if you look at any sequence of elements separated by K, they're going to be in order. If you take that same array and sort it again with a different K, which he's calling H, then you're adding the property of H orderedness to your data, but you haven't lost K orderedness either. And gives a proof I don't understand. But that's an interesting theorem. In fact, he calls it an astonishing phenomenon.
I guess the trouble I have with that, like intuitively, is what if H is a multiple of K, right? So you'd be somehow, there's a chance that you could be moving things again.
Well, if H is an exact multiple of K, so H is larger than K, then that's a no-op. Right? If it's already sorted with stride.
Yeah, if it's already sorted by K, then yeah, so that's true.
The interesting thing is that it apparently is astonishingly true, even if they're not even, like even if they're co-prime. So even if you by stride 7 and then sort it again by stride 5, it will still be sorted by stride 7.
What could go wrong though? What could go wrong? Let's say that something is 7 sorted and now we do 3 sorting. So every 7th value is now sorted. And now we reduce the step size to 3. Why would we lose 7 sortedness? Or how could we lose 7 sortedness? If somehow we moved one of the values that was 7 sorted out of order. Like if it was less than some other 7 sorted value, then after doing the 3 sorting, you've somehow moved it past that other value and created disorder. Right? Am I explaining it okay in terms of the issue?
Oh, I don't know. I guess it's all counterfactual because that never happens. But how could it happen?
Obviously, it doesn't happen because the theorem is stated. But
I think I get it. Wait a minute. If you have something that's 7 sorted, and now you go through and do a 3 sorting, you're moving things into a different subset that's 7 sorted, and it's going to stick. The 7 sortedness is going to stick because it's a different slice.
But they do overlap at some point, sometimes.
Yeah, but that's not going to matter. You think of 3 sorting as breaking the 7 sortedness of an array, but it doesn't, because if the 3 sorting doesn't move anything, then obviously the 7 sorting is still in effect. But when it does move things, it's moving things into a different slice of the 7s.
Yeah, so I guess the question is, could a 3 sort after the 7 sort, could it move something past, some, like there's a bigger value that was 7 sorted, and now between 2 of these 7 sorted values, right? So there's 6 values in between.
Yeah.
So yes. Could a 3 sort somehow take one of these, I guess, any one of these 6 and somehow put it in the wrong position past the previously 7 sorted? I think that's what he means by the dominator, right? Like there's something that's dominating based on the 7 sorting. Could you violate that domination that you've established with 7 sorting with a subsequent 3 sorting?
Apparently not.
Right, but why is that? That would be the proof.
Yeah, I think I kind of get it. I think it's like I said, you're not going to do that because you're moving these elements into a new slice, and you're doing them in order. A new slice of that 7.
A new slice of that 7? You mean the chunk between the two 7 sorted values?
If the 3 sort changes something, it'll change 1 to 4, and the assertion is that the 7 slice that contains 4, that would be 4 and 11 and 18, is going to end up in order.
Mm-hmm.
It's different than the one that you started with, 1 and 8 and 15.
It is different, but why can't it cross one of those boundaries that's been established by the 7?
So you would be putting A's.
Like, why could that not happen? That
all right. So
you could take you have two 7 sorted values, right?
Yeah. Could
the 3 sorting affect the smaller 7 sorted value and somehow?
I don't think so. Listen to this, okay?
Mm-hmm.
The 3 sorting is going to change 1, and it's going to change 1 and 4, okay? It's only going to put a smaller number into 1, but let's look at where that 4 went. So in order to mess it up, you're saying that some other element, like the one that's going to end up in 11, is going to be less than the one that you just moved into 4. Because if it was that way, then it would break 7 sorting. Well, where did the 11 one come from? The 11 one came from 4. Because it was 7 sorted. So it can't be.
Okay.
So the 11 one must be bigger than the one that you swapped out from 4. And the only reason you swapped it out is because you found something that was yet smaller. You swapped it out in the 3 pass. So in the 3 pass, you're comparing 1 and 4. And if 1 is smaller than 4, then you swap it. And your assertion is that that's going to break something further down the line, but it's not, because in the 7 sort, the next biggest item is 11, and that's already been sorted. It's already bigger than both 4 and 1.
So Arthur, your chat comment is showing a 3 sorting, and then
I'm just noodling around with numbers over here. I have
sure
entirely with means.
Yeah.
This certainly seems to be a counterexample, but again, I assume he had some reason for stating what he did. Anyway, I found it interesting.
Mm-hmm. Good enough. Okay. Did we get an answer to whether insertion sort is stable?
No one said it out loud, but I don't think that it is.
Insertion sort should be stable, right?
Oh, shell sort, I mean. Insertion sort.
Shell sort, I don't think it is. But yeah. Insertion sort will be stable if you have the right treatment of when they're equal. And that is, when they're equal, you still have to move on.
When they're equal,
he's going backwards, right?
Mm-hmm.
He's going backwards. Insertion backwards. So as soon as you find one that's equal, when that caret comes to something that's
you
equal,
just stop.
That's a good insertion.
Essentially, you don't do anything.
There. You don't do anything. You just you insert it there, and then it'll be stable. If you're looking for an item that's greater than, or if you're looking for an item that's less than for your insertion point, then it would not be stable. But on shell sort, I thought of an example. I thought of how you could see it as a counter example, but now let me think.
Okay.
If the first 8 items were maximal, okay, then what's going to happen in shell sort? No, that's not it.
Yeah, if the first 8 are maximal and there are only 9 total, for example.
There you go. There you go. That's similar to what I was thinking of. Yeah, if there's only 9, then you do an 8. You're going to swap the first one, which should end up in the first position. You're going to put it at the end of the list. And that'll break it right there. Because if you just did 8 and 1, the 1 sort is stable, because that's just a normal insertion sort. So, so if you just had 8 and 1, and the first 8 elements were maximal, and you had 9 elements in the list, then that pass for 8, the only thing it's going to do is 8 is 1 compared with 9. The 1 is maximal, so you're going to swap it. And then the 1 sort isn't going to have anything to do. So what ends up happening is that your element that was first in the list ends up last in the list, and it should end up second in the list. Because what you have is an element of 8 maximal elements followed by a smaller one. And if you shell sort it, then the order of the 8 elements that are equal cannot change. So shell sort is not stable. I don't know whether there's even an easy way to make it stable. Well, yeah, there is. Yeah, there is. You just add You just add the index number to the key.
But that takes an extra n space, right?
Yeah.
Because you have to keep track of it as it moves around. So
yeah, maybe. Maybe it does. Not necessarily, but maybe.
Anyway, I've just noticed it's 4 o'clock. I actually have to go at this point. But see you all next week.
Thanks, Arthur. See you. Okay. Yeah, so most of the other exercises are not that straightforward, and a lot of them have to do with the analysis. So if something catches anyone's eyes, we can discuss it. Otherwise, I can just go on to the step through. And again, if any of you stay on, I'm really grateful. But if you need to drop off, yeah, that's fine too. So any exercise?
For 30 minutes. I said I can stay for 30 minutes.
Okay, cool. All right, so let me set that up. I've pasted the link to the MMIX file that I'll be showing. How's the size? Everything readable? Clear? Okay, great. Right, so first I will do the insertion sort code that's from the MMIX supplement, and then we'll do the Shellsort. And they're pretty similar, especially once, as we've seen, you understand insertion sort, then there's just a little bit of changes that occur in the loops for Shellsort. So this is, as usual, a lot of these are taken from the MMIX supplement with some test data from the MMIX supplement website. So they have those files up there for you to use. And so I've just sort of combined them together. So in this particular version, the data that I'm using is down here. So this is the, yeah, so let's see. Yeah, so this is the input data. There's 10 values in there, and this is the expected output or the expected array, the sorted array. This is just for our examination visually. We won't be actually doing any verification within the program, but we'll be able to see it in the debugger. So down here, this is the little main program. It calls the sort subroutine on line 112 with the push J instruction, there's no registers that are being saved, so that's why it's a push J0, and there's no return value because the array is sorted in place. The two parameters that are expected, the address of the data array, that's being passed to register 0, meaning that the subroutine will see this address in its register 0 on the stack, and then the second parameter is the size of the array. And then up here, this is the sort subroutine, and we'll go through that. There are some register names being defined or declared up here. There's the key, which is the address of the array, or in other words, the address of the first key. And then there's, so that's in register 0. And then register 1 is what we're calling n, which is the number of elements to sort. And then there's some other register names that I'll explain as we go along. So when we start out, down here, you can see in this first memory panel, the array in memory. And we've got 10 values, so 1, 2, 3, 4, and 5. So these two rows are showing the 10 values. And this down here in the bottom memory panel is showing the expected sorted array. This is again just for visual verification. All right, so let's start the program. And yeah, I've noticed that I've been having some problems with the automatic breakpoint at main. For some reason, it hasn't been doing that. So I need to set a breakpoint myself. Get rid of this one. Okay, so let me start this again. Do this, get rid of the windows that we don't need. This one, and the special registers. What? It didn't break here either. Try this over here. It's not breaking at all. Okay, it's weird. Let me try breaking at the sort subroutine. Okay, it's breaking here. So something is up with this debugger. And all right, so let's get rid of these windows. Okay, so we did the sort push J instruction to end up at the start of the sort function, and at $0, you can see that this is the address. So it's showing in decimal because that'll be more convenient for the other values. But this is the address of the data array, which is shown down here in the data segment. And we've got these two global registers, which we don't really need. So I'll keep them around. It's okay, but we don't actually need them. So here we are at the first instruction of the sort subroutine. And what it's doing is some initialization to set some base addresses that are going to be used again and again with offsets. And if you've seen some of the MMIX code before that we've stepped through, you'll know that this is like a common pattern, that a few registers are set up to just hold a fixed base address, either of an array, usually of an array or something else. And then other registers are being used as offsets that are scaled by whatever the word size is of interest. So in this case, all the values are 8 bytes, octabytes. So every offset will be scaled by 8. And so that's what's happening here. Key is the base address of the array itself, of the first key. And so key 1 is actually going to be the address of the second key, because that's where we want to start our outer loop. And so we'll use that as the base address, and then every time we increment, we'll just add something to this key 1 base register. So we step over that, and then in the next instruction you can see that there's this 8 add u, which is a very nice instruction to do scaled offsets arithmetic for addresses. So this is going to multiply the second operand by 8 and add the result to the third operand. So this is a nice way where, if you have a base address, you can keep that as your as your third operand, and then anytime you need to do an addition that's being incremented, you can use this sort of instruction. And obviously, because we're dealing with octabytes, so we're using 8 add u. But if we were dealing with 32-bit quantities, then we would do a 4 add u and something similar. Okay, so that will give us the address of the end of the array. So that's 1 past the last key. And this d in the next instruction is set up to be the distance from the second key to the end of the array in octas, right? Because these are now addresses, both of the registers key n and key 1. And then this distance is going to be used to move one of the counters, as you'll see. So this is just some initialization, and then we initialize the actual outer loop counter j, which is in $2, and this is going to be a negative offset. So if you remember, in insertion sort, the outer loop starts at the second key and moves up to the end of the array. And the way they've got it set up in the assembly, it's using a negative offset from the end of the array, and then we'll just keep adding, octabytes to the counter and move it up towards the end of the array. So when it becomes 0, that means we've reached the end of the array. Okay, so when I do this, you can see that j has become -72. So there were 10 values in the array. Each value is 8 bytes, so that's a total of 80 bytes. So if you are starting from the second entry and all the way to the end, that gives you -72. And this is all set up to start the first iteration of the nested loop. So we jump into the loop to S1, and S1 is essentially the guard of the outer loop, and this is a probable branch because it's likely to be taken. It's just a linear scan. The outer loop is just going to start at the equivalent of j equals 2, and then it'll just keep incrementing. So we won't fall through until the very end. And so now we take the branch and we start the actual first iteration. So what are we going to do here? We need to get the keys that we want to compare. First, we want to set the key for the outer loop, which I'm calling the outer key. And so that is being loaded into register 4. So if we look down here, the first key is this 5. The last key is also a 5 down here, right? There are 10 values. So the first key that we're going to start for the insertion sort will be the second key. So we should be loading a 3 as a result of this line. And how is that going to happen? Again, the j is a negative offset because we are going to add it to the address of the end of the array. So, this is the end of the array. The negative offset will bring us back to the second key. So that's what we should expect to see in register 4 is the value 3. So let's do that. Okay, so yeah, that's exactly what happened. So register 4 ended up being 3. And now we've got our first, fixed outer key. And the goal is now to compare it with all the keys before 3 or lower down in the array. And so for that, first of all, we need to start that inner loop. So that counter is initialized. And this should end up being the offset of the first key, which is 0 within the array. And so $3 just happened to be 0 from before, so that's why it didn't get highlighted. All right, so then the next thing we need to do is to actually get the key value, the value of the key into one of the registers, and that register is going to be Ki. So Ki will hold the actual value of the key at the entry corresponding to I. And in this case, we know that we're starting with the second key, which is 3. And so the first comparison will be with this value 5. So we should expect to see that in register $8. So let's do that. And so that's what happened. Sorry, dollar, I think I've mislabeled this. This should be $5. Let's just confirm Ki. Yeah, Ki is 5. So that's a typo I need to fix. And okay, so that's where we were. And now we can do the comparison between K. We compare K, which is that outer key, to Ki, which is the inner key. In this case, 3 compared to 5. 3 is not greater than or equal to 5, which means that we'll need to move 3 down. The way it's done is to move 5 up and just keep 3 in the register. So it'll just stay in the register until we find its correct position. But while it's traveling, each of the values that it needs to skip over gets moved to its virtual current position, right? So in this case, we expect to see a -1 as the comparison result in $9. And that's what happened, okay, because 3 is less than 5. So what that means is that now 5 has to be written to memory where 3 is supposed to be currently. As it happens, 3 is right there, but if we had more values to compare, you'll see that happening. So, we're just keeping track of where 3 is supposed to be so far, and then anytime it needs to move further, we just take that value that it compared to and move it up in the array. So that's what's going to happen here. We branch to the piece of code that is going to store key 1, place it into memory where 3 is supposed to be. And 3 is at this index 1 if we are counting from 0. So in memory over here, we should expect this to be replaced with a 5. So yeah, so that's what happened. So that got replaced with a 5, and so now we decrement the outer counter. We decrement the inner counter and check if there's still some more values to compare toward the beginning of the array. And we'll find out that there aren't any. We're at the beginning. And so in that case, we're done with the inner loop. And in that case, we need to update the outer counter as well. So we do that. We increment the J counter by 1 octa, which, if you look at the value, means decreasing its negative offset from the end. So from minus 72, we should go to minus 64. And so that's what will happen in $2. So we see that happening. Okay, so now we check if we're at the end of the array, or are we done, or do we still need to continue with the outer keys? And in this case, we do need to continue, so we go back for another pass, for another iteration, and we load that outer key, which in this case is going to be the value in the third key, so over here, so which is 2, right? We started at the second key, now we're at the third key, and so this 2 will be compared to everything before it. So that's first comparison will be to 5, the next comparison will be to 3, and then we'll be at the beginning of the array. So 2 should end up as the first key after the inner loop is done, and it will cause 5, first of all, 5 to take its place here. And then virtually it will be, when that swap happens or when that movement happens, 2 will be at this point, and then it'll be compared to 3, and it'll turn out to be less than 3. So then 3 will move up 1, and then 2 will end up in the first key position. So I'm just going to step through that and see that happening. And in memory, at some point, we should see, yeah, so we see the 5 as the third key now. But if you'll notice, the second key has not changed because we're not actually writing the outer key to memory until we find its final correct position. But virtually, the point we're at is this point. So now we're going to compare it to 3, and then we'll find that 2 is less than 3, which means that 3 moves up, and then we'll find that we're at the beginning of the array, and at that point we're going to write the 2 to memory. So now we've got the first 3 entries sorted. We've got 2, 3, and 5, and we're going to continue with the next value, moving 1 up for the outer counter to key number 4, which is another 5, and so that is going to be compared first of all with 5. So this should be a little interesting because here the 2 keys will compare equal, and let's see what happens there. So we do the same thing. We load up the outer key, and then we load up the inner key, and we find out that back here, when we did the comparison in $9, we got a 0, which meant that the 2 keys were equal. So this branch was taken because it's branch non-negative, which includes a 0 result. And so we ended up at S5, which is over here. And so this one is saying that key and key 1 turned out to be the same. And so, or sorry, not key 1, but ki and key turned out to be the same. Is it key or k? I think it's k that we're calling. Yeah, so K is the register that holds the outer key. And so we're just going to write it to memory to the location where the value that we compared to that turned out to be equal is, right? So in a sense, this is redundant. We don't really need to do this. We know that the keys were equal, but we're still writing it to that memory location. So we do this, and then we are essentially going to stop with the inner loop because we're done with the comparison to all of the entries before the outer key. So we go back to another iteration of the outer loop. We load up the next outer key, which after the 5 is the 7. So now we have the 7. 7 will turn out to be greater than the first value it compares to. So again, something very similar is going to happen. Here we get the 5. We do the comparison. 7 is greater than 5. So we do get a +1 in the comparison result register, and we end up with writing that outer key to memory. And so over here, again, we won't see anything changing in the debugger because that value is already 7. So that's what happened here. And now we go through another iteration of the outer loop, updating the counters. And the next key to compare or to fix for comparison is this 11. And that's loaded up in register 4. And we get the inner key, which in this case is going to be a 7. That's the first inner key. And we do the comparison. 11 is greater than 7, so the comparison result is 1. Didn't get highlighted because the 1 was there from the previous iteration. And then we end up doing the same thing. We just basically are writing that same value to memory where it already is present. So we're done with another iteration of the inner loop. So we update the outer counter and go back to the beginning of the outer loop. And now the next key to load will be this -3. And we can see that, -3 compared to the portion of the array that's been sorted so far before -3 is -3 is going to be smaller than all of them. So this is going to cause all of these 6 values to move up one by one. Okay, so let's see that happening. We load the -3. We start the inner loop at this key. This is the first key to be considered for the inner loop, and we load the key itself. We get an 11 in register 5, and then we do the comparison, and remember we're comparing -3 to 11, so the result will be -1 down here, and that means we now have to write, or we now have to move 11 1 up in the array. And so that's what's going to happen here. The inner key is written to memory, and we see that in this panel. So the 11 took the place of -3, and -3 for now is not visible in memory anymore because it only exists in the registers, in the register that's being used for the current loop, and it won't get placed into memory until we find its correct position. So let's do that, keep stepping, and I'll just step a little faster here, and you'll see each of the values moving up in the array. So the 7 moved up, you can see that down here, right? So just keep your eye on this memory panel, and we'll see that happening. So in fact, what I can do is let me just put a breakpoint here, and then we don't have to step over each instruction. So let's do that. So after 7, we should see this 5 moving up here, and then this other 5 take the place of the first 5, and then the 3 take the place of 5, 2 take the place of 3, and then -3 finally becoming the first key. So let's do that. Okay, so 5 moved, then 5 moved again, but nothing got highlighted because it was already 5, and then 3 moved, and then 2 moved 1 slot higher, and now let me disable this one, and let's see where -3 ends up. So at this point we go back for another iteration. I think that we probably skipped 1 full iteration, but we are now at the point where oh yeah, that's right. So after the 2 got written, we found out that we were at the end of the inner loop. So at that point, we're just going to write the outer key to memory. And so that's what happened here. We get a -3 as the first key. And so what's left? Everything up to this point is sorted. And so we only have 3 values left, 2, 99, and 5. So 2 is going to move down a few positions up to this point, and so everything else will be moved up. So I guess we could just keep this breakpoint here. Outer key or inner key, maybe here. Yeah, let's put a breakpoint here, and so we should see the movement right away. Okay, so 11 moved up. Remember, the current key that we're the outer key that we're looking at is 2. So 2 is less than 7, so 7 moves up. 2 is less than 5. 2 is less than the other 5. 2 is less than 3. And at this point, 2 is not less than 2. And so that's its correct position. Then what is left? We still have a 99. So three, 4, 5, 99. What was our the original array is 2, 99, and 5. So we are at 99. Why did this 11 move up? That's a little unexpected, so I'm not sure why that happened. But let's see if we continue and it does the right thing. So 7 has moved up. And it stopped. I think my breakpoint at some point is causing a whole bunch of things to run that I wasn't expecting. But yeah, so, but this doesn't look right. -3, 2, 2, 3, 5. Were there 3 5s? Yeah, there are 3 5s. So that is not right. -3, 2, 2, 3. This is correct, up to 5, but then over here, the third 5 is missing. And then 7, 11, 99. This 7 is wrong. This should be a 5, and it has terminated. So let's see if we can figure this out. Let me run this again. Okay. Let's put a breakpoint. Let's get rid of a couple of these windows. Okay, so let's put a breakpoint when this returns at this pop. Okay, so I'm going to put a breakpoint there, let it run, and let's see, we've got 1. Yeah, so the original data array looks right. I've got the 3 5s in there. Let's continue. This time it's right. So I have a feeling that there was some sort of garbage that got placed into memory when the previous run terminated for some reason, because this is showing correct output. This is, at the end of the subroutine, just before it returns, we can see that the array in memory has become -3, 2, 2, 3, 5, 5, 5. There's 3 5s, and then 7, 11, 99. So that looks okay. So I think, there's something that happened when I had set that breakpoint, and when the subroutine terminated, something got written to memory, after the termination of the program, and it just seemed to suggest that the final values in the array were not correct. But I think that was just some artifact of the debugger. So I wouldn't worry about it. But we can run this maybe another time and just make sure that is consistent. So let me click this to halt execution. So I can just step through this. So step here, we return to main, and then step here. Now we've halted. So the program is terminated, and let's run it again. Do we still have the other breakpoint? Yeah, we still have the breakpoint at the return over here. So let's run this again. So let's run this. Okay, so there's a breakpoint at the entry to the function, and there's a breakpoint at the return from the function. So first breakpoint, we should be able to see the unsorted input array. So let's do that and close this window. Okay, close this window, bottom. Okay, there. So unsorted array 5, 3, 2, 5, 7, 11, minus 3, 2, 99, and 5. So this is correct. Continue to the return from the subroutine. We have minus 3, 2, 2, 3, 5, 5, 5, 7, 11, 99. Okay, so things look fine as far as insertion sort goes. And yeah, so I think for now, we'll just do this, and I will record the Shellsort step through later because this session has gone on for a bit longer than I expected. So what is next? Let's see. Let's see. Let me finish up with a couple of the slides that I had. Okay, so this is where we left off in the main session, and right, so our next meeting is next Saturday, the 5th of December, and we will be going over section 522, which looks at bubble sort, a couple of variants of bubble sort, merge exchange sort, and that's about it. So hopefully I will have a Shellsort step through available for you, and then we will be able to do another step through for one of the programs, one or maybe two programs from next week's agenda. And as usual, you know, we have all our recordings and videos on our YouTube channel, and all of our work is available at the GitHub repo. There's a whole bunch of meetups by now. This was our 13th meetup, I think. And so all the chat copies are there. And by now, you know, there's quite a few MMIX programs for you to look at. And I've also written some C implementations, which are available in the programs repo of the algorithm. So you can, you know, you now have the possibility of understanding TAOCP, following TAOCP and the algorithms in C. And of course, you have the original MMIX as well, that those programs have been contributed by Martin Ruckert. I've also written a couple of other MMIX programs that are not from the supplement. So there's quite a bit of material that's slowly accumulating, and you know, the only thing now is really just whatever your level of interest is. But the resources, I believe, are, at least to get started, I think there's quite a bit of material now, and we are getting into interesting stuff, sorting algorithms. And you know, you can go back to some of our initial videos and meetups where we sort of discuss the direction that we're taking. But just to recap, we're not going through the entire TAOCP, you know, strictly sequentially. We're following sort of a goal of getting to the more advanced material as reasonably fast as possible. So what that means is that we do just enough data structures to allow us to look at and study as many of the algorithms as we can, just to help us get us as far as we can with certain data structures. And right now, all we're relying on are arrays and lists. So Knuth calls arrays sequential lists, and the other kind would be linked lists, singly linked lists. At some point in a few meetups, we will need to go back to the basic data structures, look at doubly linked lists. Those are pretty important, and they do come up a lot in some of the more advanced stuff. And then, the biggest data structure that is sort of the basis for so many algorithms, especially in Knuth's work, are trees. So we'll be doing trees, different kinds of trees. And then hopefully at some point we'll also reach graphs. But again, in the meantime, we'll do some data structures, then we'll go to as many algorithms that we can cover with those data structures. And then, yeah, just keep going back and forth. So hopefully you enjoyed the video, enjoy the meetups. If you can join our meetups, that would be the best. But if you can't, I hope you do make use of any of these resources, and do let me know, do let us know what you think of the videos, what you think of the meetup, what you think of our work and discussion in comments, in YouTube. So that would be really great. Thank you very much. And again, I want to thank everyone who showed up today, Michael, Arthur, Jolene, and Miguel, because, as I've said before, even if one person shows up, I'm really, really grateful. But to have, so many people attend regularly, that's just fantastic. All right. Thank you. Bye-bye.